Good morning. Hey, good morning. I am constantly refreshing the weather. You know, just in case. They've changed our forecast so many times. Are you frozen?
Huh?
Are you frozen?
Yeah. Partially. This is gonna like snow.
Yeah, now it says snow possible around 12 p.m. That's what this is saying. So we're gonna try and move today, like move it along. Hey, hey. I don't trust these predictions. I think this thing is too variable. Yes.
I thought I knew that it was this and it I just looked at my fingers. Absorb. I messed it up.
Okay, yeah, I see what you're saying. Yeah. Think of it this way. Well, you're an exotherm because you're warm, right? So you're releasing energy. Let's see.
Exothermic is like that fire, right?
Um, kind of. Yeah. Well, yeah.
Is it a real fire?
It is. It's a gas fire, but it's
Imagine
fire.
it was like it's kind of
It is there's a reaction going on.
Imagine if it was
Combustion. Yeah, it's combustion.
Imagine if it was a grease fire.
Ew, those aren't fun. Grease fires, not fun.
Can you put them out by putting milk in it?
I would not do that because milk, it will spread it just like water. You should use a fire blanket, a fire extinguisher if you don't have that flour for a grease fire. Just throw flour on it, it smothers it. Yeah.
Fire extinguishers instead of water. Turning off fire.
Depends on the fire. So like she was just saying, if it's a grease fire, like say you're frying chicken and your oil catches fire, which happens sometimes. If it gets too hot, it just catches fire. You put water in that, it's going to spread out, make your fire even bigger because oil and water don't mix. So the water will go underneath and spread the oil out, right? Because the oil will float because it's less dense than the water. So it'll just spread it all over.
So how do you turn it off?
You got to smother it with something. So you either smother it with a fire extinguisher, you smother it with a fire blanket, a lid, or flour if you don't have anything else. If you got flour in your kitchen, you can throw flour on it and that'll smother. Actually, my son, he was making fried chicken for his friends at school and some of it dripped off and hit the burner and started a little fire. And his instinct was to get a cup of water and his roommate was like, no, 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 don't do that. And grabbed a cookie sheet. So my kid picks up the cookie sheet and slams it down on the fire and he's like, and it worked, but then it burned my hand. I'm like, yes, it would have. So he's like, so my hand got burned, but I put the fire out before we burned down the apartment. I'm like, well, that's good, honey. You live, you learn, you know.
Does he still have his hand?
Oh yeah, I didn't burn it off. It's not like he went to a crematorium. He just it was painful for a couple days, but hey, you live, you learn.
Did he have to put ice on it?
I think just cold water was enough. Cold water is better. Ice can damage your tissue, so you don't want to put ice on it. You just want to put cold.
One time, like, um, one time, Dad brought potato kids over. Well, one time, well, that Dad was holding up like tray with tinfoil and hot potato skins right out of the
Yeah.
oven, and I was sitting right here and it burned my knee a little.
Oh my, yeah.
Fire, you smash two metals,
Some metals. Yeah, we can make sparks for sure.
my nails, like, when I
Mhm.
was trying to make a wooden box.
Oh, did you make
and
sparks?
I made a lot of sparks.
Mm-hmm. Emerson, are you willing it to snow with your t-shirt? You got a snowflake on you. It's like you're willing it to snow. Are you hoping it will snow? Yeah.
Yeah, I love snow.
I love it too, but I don't like it when it's this unpredictable. Like it makes me anxious because I've got all y'all here and I'm like, please don't start snowing. And then I don't know whether or not I'm gonna make it to Marietta this afternoon like I'm supposed to because I don't know how it's gonna look. So I guess we'll just have to play that out. All right, well, we will go ahead and start since it's 10:01. I think Lucy should be here, but maybe she's just a little slow today or whatever. Okay, so we're doing gas.
Little snow.
Yeah, but I don't think there's been any around here yet. I heard there was some, definitely south and west of here, but the what?
The river.
No, it takes a lot for the river because it's got to be really, really cold for a really long time because the water's moving. Yeah, it's got to be colder than that, and it's got to water that still will freeze pretty easily, but water that's moving is harder because it's constantly in motion and the particles are moving about. You got warmer patches and cooler patches and okie dokie. Let's have a look here at gas behavior. This is our last lesson of Unit 6, isn't it? You've got a test this week, people. Hooray, hooray. Now, I'll tell everybody in case anybody missed it, but I sent out an announcement this morning that said we are going to be working on an accelerated schedule today because of the weather. So that means you guys, your class is going to be normal, but with lab, as soon as we wrap up lab, as soon as lab is done, you may leave if your ride is here. So if you have a phone, you can text your mom or dad and say, hey, I'm done. If you don't, you can tell me and I will text your mom or dad, okay? So everybody understands we're probably going to end lab before we typically do. So if you need me to text your parent for you because you don't have a phone, this doesn't apply to you because you got to wait on your brother. Then I will go ahead and let them know we're done if you want to come grab early. Okie doke, are we ready? Let's just roll through this. Lesson 20, gas behavior. So first, we're going to talk about when the pressure of a gas is constant. So today's lesson has a lot to do with pressure, volume, temperature, and how they're all related to the way gases behave. So when the pressure is constant, this is one framework for Charles's law. So Charles's law states that when the pressure of a gas is constant, if the temperature of the gas increases, what happens to the volume? Eunice?
The volume,
Increases. Yes. And when the temperature decreases, what happens to the volume, Emerson? It will decrease. Okay. So when one thing goes up and the other thing goes up, or one thing goes down and the other thing goes down, we say they're what proportional? Directly proportional. Okay. We have direct proportionality and indirect proportionality. So if one goes up, the other goes up, or one goes down, the other goes down. That's direct, right?
They're running the same. And if one goes up, the other goes
like
down.
if making Emerson happy makes me happy, that's directly proportional. But if making Emerson mad makes me happy, that's indirectly proportional, right? Because she's going one way and I'm going the other. Inversely proportional. Inversely. Sorry, I didn't say indirect. So this shows that if one goes this way, the other goes this way. If one goes this way, the other goes this way, right? If one goes left, the other goes left. One goes right, the other goes right. One goes up, the other goes up. One goes down, the other goes down. All right. So when you look at Charles's law mathematically, it looks like this. So calculations using Charles's law involve the change in either temperature or volume from a known starting amount. Okay, so when you see the subscripts, so V sub 1 and V sub 2, T sub 1 and T sub 2. V sub 1 is going to be your initial starting volume. It's what you know. right? And T sub 1 is going to be your initial starting temperature. And then T sub 2 and V sub 2 are going to be what you end up with. It's like initial and final, sub 1, sub 2.
They're both equal as you can divide the two, so because 2 divided by 2 equals 1, so.
Yeah, so it's kind of like, sort of like, but it's kind of like the, if you were to think of these as fractions. So imagine that V sub 1 over T sub 1 is 1 over 2. If we multiplied that by 2, we would get 2 over 4 because they're directly proportional. They're both going up together or they're both going down together. Okay. So, yes, ma'am.
So if you look outside, you'll see a male cardinal.
Yep.
I also saw a female cardinal and a chickadee.
Oh, you know your birds. Yep. I've got, well, that's a camera too. That bird feeder is a camera and it posts amazing videos of them and photos that are, I think, 2K. So they're pretty good quality.
Yeah.
It's a lot of fun.
Birds
Yep.
are so cute.
They are. But let's try to stay focused on our lesson. I could watch them all day, but we'll try to stay focused on our lesson. Okay, so the first thing is Charles's Law was named after Jacques Charles. So we're going to learn a quick bit about Jacques Charles.
Ever wondered about the fascinating life of Jacques Charles? Born in 1746, he was a French inventor and scientist. Charles made significant contributions to the field of gas law. He invented the hydrogen-filled balloon, a game changer. His first flight in 1783 was a spectacular success. Charles also explored the properties of gases and their behavior. Despite challenges, he continued to innovate and inspire. His legacy lives on in science and ballooning today. So, what can we learn from Jacques Charles's journey?
Well, here's something we can learn. They said he invented what kind of balloon? Hydrogen balloon. Okay, hydrogen gas, is it really dense or really not dense?
Not dense.
It's not dense. It's the lightest gas we have, right? It's tiny. It's a tiny little atom, right? It's a little molecules, H2 or tiny. Okay, here's the problem with a helium balloon. All right, I'm going to show, hydrogen balloon. I'm going to show you this dude. This guy is one of my favorite guys on Instagram. His handle there is Big Manny. He's British and he is a chemist and he does lots of little experiments for you to see how chemistry and science work. But he has the thickest British accent and British slang. So like you'll hear him say in it a whole lot, like this is hydrogen in it, isn't it? But he says in it. And he says it at the end of every phrase. It's like just part of how he talks. It's hilarious. So anyway, this is the hydrogen balloons are great because they're going to float, right? Because they're less dense than the air around them. But this, watch what
I've got a
happens.
balloon there, and I'm going to fill it up with hydrogen gas and then blow it up in it. Obviously, I need to make some hydrogen gas first, innit? So I've got some hydrochloric acid there, and I'm reacting it with copper sulfate. This creates some green copper chloride. Then I'm going to add some aluminium foil to the copper chloride, and it's going to react to produce aluminium chloride plus hydrogen gas. And all of the hydrogen gas is going to be bubbled into this nice green balloon here. You're done though, we're filling up. Come on, you know what time it is. Boom, yeah, let me take it off now. Wrap that up in that, and then I'm going to tie a string to the end, innit? Then I'm going to light the string. I'm going to see what go on, innit? Let's go. Oh my days, we're lighting up. Cool, yeah. The flame is moving up the thing still. Listen up here. Let's see what pops off. Big explosion things.
Big explosion things. I love him, man. So Big Manny just blew up a hydrogen balloon because hydrogen is what? It's highly flammable. Okay. So back in the day, when we first started our adventures in ballooning as a human race, we used hydrogen balloons. And probably the most famous airship with hydrogen that we still know of today is the Hindenburg. And the reason we know about the Hindenburg or remember it today is because this is what happened to it.
Hindenburg airship approached its landing in Lakehurst in New Jersey. The world watched in awe. It was the largest airship ever built, and its luxurious interior and ability to travel long distances without refueling made it a marvel of modern engineering. But in 1937, as the Hindenburg was preparing to land, tragedy struck. A spark ignited the high-rich gas that kept the airship aloft, causing a massive explosion that sent the Hindenburg crashing to the ground in flames. The disaster claimed the lives of 36 people, including passengers and crew members, and left countless others injured. The disaster signaled the end of the airship era. The development of airships for commercial passenger travel ceased. Today, the Hindenburg disaster stands as a sobering reminder of the importance of safety and vigilance in all forms of transportation.
So we don't use hydrogen balloons or hydrogen airships anymore because that happens. All it takes is a tiny spark.
That's scary.
And that is one of the like greatest like travel disasters in human history. It was a big
Ever
deal.
wondered about
Engineering
fascinating
disaster.
level
Okay,
of-
everybody go. Woo! Sorry. Yes,
Is which is less dense, hydrogen and helium.
hydrogen is less dense because it's your first on the periodic table, right? Number one, so it's going to be smallest, so it's less dense. All right, now. When the volume of a gas, yes, is that a constant?
When the volume of the gas is constant, the temperature and pressure go up and the temperature and pressure go down.
Yeah, if the temperature of a gas increases, the pressure increases. And if the temperature of a gas decreases, the pressure decreases. Anybody have an Instapot or another kind of pressure cooker?
Yeah.
This is what happens. You put the lid on, and this is at a volume is constant. When you lock that lid in place and close the little vent, you've now fixed your volume, right? Air can't come in and out. Gases can't move in and out. You've got a sealed system inside there, right? And then you increase the temperature, what happens? That pressure goes up, 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 up. Why? Because all those particles are now getting more energy because remember, what is temperature? What's the definition? It's the average kinetic energy of the particles in a substance, right? So you're increasing the energy, you're increasing the motion of the particles, they're bumping into each other. That's friction. It's creating even more heat, right? Bounce, 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 bounce. And they're spreading out because they're banging into each other. That's what makes your food cook faster because now it's under pressure. So it's like really getting like all that heat is getting transferred into that food. And it also makes your like if you're putting meat in there, it gets really tender, right? If you had meat from a pressure cooker, like chicken or whatever, gets really, really tender because all of that pressure and heat breaks down the proteins to some degree and the fibers in the muscle of whatever meat you're eating, and that makes it much more tender. All right, so in this case, again, we have temperature goes up, then pressure goes up, and they are what kind of proportional? They are directly proportional once again. So we see the same little graphic. Up, left, right, down, right? Same little graphic. All right, so then if you look at this as a math equation, this is called Gay-Lussac's law, right? That's what we're talking about. So calculations using Gay-Lussac's law involve the change in either pressure or temperature from a starting pressure. So P sub 1 is going to be what kind of pressure? Your initial, and P sub 2 will be your final. So sometimes in like physical science, we will do like instead of a sub 1 or sub 2, it'll be a sub I and a sub F for initial and final. V sub I, right, your velocity sub I minus your velocity sub, yep, exactly, V sub F. So it's the same thing. Sub 1, sub 2 in this case is the same thing as, because what you're not doing math with that 1 or 2. It's telling you that it's a different piece of data. It's your starting and ending, right? Like if it were an exponent, if it were superscript, you'd be doing math with that number, right? Right. Okay. So now this is called Gay-Lussac's law because that's the man's last name. It's hyphenated, Gay-Lussac. Okay, it's his first name isn't Gay. I did know a lady whose first name was Gay once, G-A-Y-E. But Gay-Lussac is his last name. It's hyphenated that way, like it's two last names. I'm gonna skip this guy because we're gonna actually do this one in lab. But this is interesting. Gay-Lussac, Joseph Louis Gay-Lussac, so another Frenchman, he actually did a lot of things. And what he's best remembered for is this law, but he did a lot of things. And it's so funny, this video is like a really goofy and ridiculous song this guy made up about Gay-Lussac, but it tells you a lot of the other things he did. But it kind of claims that he's not celebrated. I don't think that's true. We all know Gay-Lussac's law.
When you said it's a goofy song, that reminds me of the 100 Digits of Pi.
Oh, yeah.
song.
So watch this one. It shows you all the things he's done.
Strauss, it starts with it, that's it, that's right, you took it every day lesson. So it did great work, I must improve, so in Java he was 71, 30 projects, 101, Joseph was never beaten, and yet he's not celebrating.
So he co-discovered boron
So,
and iodine.
Most important discovery of about the whole it's just the water thing, it's down of two big rocking things, figure is game or something.
So he figured out how much alcohol was in a liquid.
But now, you don't let know of competition. First, then the reason that he was throwing out gas. The bigger Bible, so it did great work, I must agree. So John he was 71, but his projects were other one. Joseph was never beaten, and yet he's not celebrating.
The burette, you're gonna be using burettes in a few weeks.
That was his game. If he was not to run Jamaica, he's not sorry. Should have got to the top 10. Went up to the skyline after the final of the app.
So he took a hot air balloon up into the atmosphere and determined the composition of the atmosphere.
So we John he was 71, but his projects were one. Joseph was never beaten, and yet not celebrating.
All right, so also if you are to watch the little video of the Gay-Lussac's law demonstration, which we are going to do in lab today, it made me giggle because the kid doing the demonstration called him Gay Lucas and not Gay-Lussac, and I'm like, that's not even close, but we tried. Okay, we're gonna keep on. We'll keep on here, and then I'll come back to you in a minute. Okay, Annabelle. All right. So when the temperature is constant. So we've done the last one we did was when the volume is constant, right? So now we're doing when the temperature is constant. Okay. The first one was Charles's law is when the pressure is constant, right? Gay-Lussac's law is when the volume is constant, and now Boyle's law is when the temperature is constant. Okay. Now sometimes you'll see this called Marriott's law, but usually it's Boyle's law. That's who gets the attribution for the most part. So when the temperature of a gas is constant, if the pressure is increased, what happens to the volume?
It decreases.
It decreases. Okay. And if the pressure is decreased, what happens to the volume, Everly? Everly. It increases. Okay. So have a look here. If you have a soda bottle and it is under pressure inside with the cap on, it just looks like liquid Coke, right? But what happens when you turn it and open it? What's the first thing you hear? What do you hear when you open a, right? What's happening? The gas is getting, yeah, there is gas that is dissolved in the liquid of your soda, right? And when you release the pressure, that gas comes out. You've now decreased the pressure, so your volume is increasing, and that you can see the bubbles begin, right? All right, so that means that volume and pressure, what kind of proportionality do they have? Annabelle?
Well, wait,
Yeah.
hold on. Inversely.
Inversely proportional. So far we've had direct, now it's inverse. So look at that graphic. One goes up, the other goes down. One goes left, the other goes right. One goes right, the other goes left. One goes down, the other goes up. Right? Right. So for Boyle's law, the calculations look like this. So calculations using Boyle's law involve a change in pressure and volume, which we're going to do as P sub 1, P sub 2 from your starting points at P sub 1, V sub 1. Now, what's different? Before, what did our equations look like?
It was P divided by V.
Right, it was division. And what's this mean?
Multiplication.
Right, when there's no symbol and you put your variables or your numbers side by side, you're multiplying, right? Yeah, sometimes you'll put a little dot in between them, or sometimes you put the little multiply symbol, and sometimes it's nothing, or sometimes one's in parentheses. Mhm. Yes, it would be. That's why we just avoid using it entirely. So when they're side by side, you are multiplying. All right, let's have a look here. Here is Robert Boyle. All right. What can we learn about Robert Boyle?
He's old.
Yeah, well, he's got a great wig.
Robert Boyle is known as an important scientist of the 17th century. Boyle, one of the founders of modern chemistry, is recognized for his studies on the behavior of gases, playing a significant role in the development of gas laws. Additionally, Boyle formulated a fundamental principle explaining the relationship between pressure and volume, known as Boyle's law. Boyle also contributed to the development of many important scientific instruments, such as the alcoholometer. His works laid the foundations of modern chemistry and greatly contributed to the advancement of science.
So we're talking 1600s. Now, this next little biography on Boyle is going to tell you something interesting about him. And I always want you to keep this in perspective. A lot of people like to think of science as being sort of anti-faith, that they don't go together. But always remember that there are plenty of people who think they do go together. And it's important because a lot of the world's most historically renowned scientists fall into one of two categories. They're either independently wealthy or they're religious, often to the point where they're like monks or priests. And the reason for that is because those people, does a monk or a super wealthy guy have to spend all day out in the field, digging in the dirt, planting things? Is that how they spend their time? No, they don't have to do that. They don't have a family to feed. And if they do, they have like if you're really rich and you have a family to feed, you don't have to be the one that's going out there toiling in the field, right? These are people who have time on their hands. And because they have time on their hands, they can think a lot. They also have resources. So a lot of our greatest scientific discoveries are people who are either monks, priests, independently wealthy people, not always, but a lot of the time. So Boyle is going to fall into the category of people who feel that science and faith are not separated. Other people that would fall into that category, for example, would be Galileo Galilei. You remember Galileo?
Yeah.
The guy who discovered.
A lot. He did a lot of things, but he also said, well, you know what? I don't think the sun is the center of the universe. I don't think the earth is the center of the universe, the center of the solar system. I think the sun is the center of the solar system. Galileo, because he claimed that earth was not the center of the solar system, that the sun was, that put him at odds with the Catholic Church, who was running the country he lived in. And it became a big deal for him. His daughter was a nun. So he never saw it as one opposing the other. And another person we will talk about next year, who was a monk, who was also probably made one of the greatest contributions to genetics, is Gregor Mendel. Gregor Mendel did experiments with pea plants. And what we understand about basic genetics comes from his experiments. So here's Boyle. And just keep in mind that a lot of people, I'm not saying you should have this perspective, but a lot of people do have this perspective. Yes, Annabelle?
Boyle's last name is funny because I know it's spelled differently, but it's pronounced
Bubbling.
Boyle.
Yep.
What's something people don't know about Robert Boyle? He revolutionized both science and faith. Born in 1627, Robert Boyle wasn't just any scientist. He's the bloke who gave us Boyle's law, the foundation of modern chemistry. But here's the twist. Boyle was also a devout Christian apologist. He believed that studying the natural world was a way to glorify God. His pioneering experiments in chemistry weren't just about discovering how things work, but also about understanding the Creator's grand design. Boyle argued that science and faith are two sides of the same coin, each enriching the other. Thanks to him, we've got a legacy that blends curiosity with spirituality. So, next time you think about the divide between science and religion, remember Robert Boyle, the man who bridged that gap with brilliance and belief.
So he's actually one of many who've done that. So always keep that in perspective. There are plenty of very religious people who think of science as being anti-religious, and there are plenty of very sciencey people who think of religion as being completely anti-science, but then there are a whole other group of people who think they go hand in hand. What you believe is your business, but know that is definitely, that it's not always one or the other. Sometimes people will go for both. Okay, here's Boyle's law in action inside your body.
Pulmonary ventilation, or breathing, is induced by changes in the volume of the lungs and the air pressure within them. During normal inhalation, the diaphragm and external intercostal muscles contract and the ribcage elevates. As the volume of the lungs increases, air pressure in the lungs drops below atmospheric pressure and air rushes in. During normal exhalation, the muscles relax, the lungs become smaller, pressure inside them rises, and air is expelled. Boyle's law explains this relationship between volume and air pressure. An increase in the volume of a container lowers the pressure of the air inside. A decrease in the volume raises pressure in the reduced space. The body's demand for more oxygen can change normal breathing to forced breathing. Additional muscles increase the changes in volume of the thoracic cavity so that more air can pass in and out more rapidly.
Y'all thinking about your breathing now?
Yeah.
Yeah, everybody's thinking about it. But
Yeah.
that's what happens when your diaphragm and all of these intercostal muscles, they contract. And when they contract, they actually open your lungs, which decreases the pressure and it becomes less than atmospheric pressure. And air is sucked in by vacuum, essentially. And then when they relax, all those muscles relax, they force that air back out because now the pressure in there is greater than atmospheric pressure and it's trying to equalize. And your body does that autonomically. You don't have to think about breathing, but sometimes you can think about breathing and you can, that's the forced breathing. And that will actually, you can expand your lungs more, right? So Boyle's law is how you breathe. And they're going to do this again. Okay, so now we have something called the combined gas law. So we're going to take the three we learned about so far, and we're going to pop them all together in one big math equation. Isn't that fun? So there is our Charles's law equation. Do we all agree? And our Gay-Lussac's law equation. Yep, recognize that. And our Boyle's law equation. So what happens if we combine these mathematically? Well, this is what we get because P and V are on top all the way across. Do you agree that P and V are on top here because there is no bottom, therefore they're automatically on top? It's like saying 1 or 1 over 1. It's still 1, right? Because you're one, this is what's on top. And what's on bottom? T1 and T2 are on bottom. So when you put these together, this is what you get.
What about the P1, P2, V1, and
Yep,
Oh.
right. P1, P2, V1, V2,
Yeah.
T1. So when you put them all together, you get this. Now, here's the cool thing. When you combine them, it really gives you some ideas of how a gas is going to behave. So we also have what we consider the constant. What is the constant? Okay, the constant is whatever you multiply them by. Remember when I said for like V1, V2, if it was 1 over 2 on one side, and then on the other side of the equal sign, it was 2 over 4, what did we multiply by? 2. 2 was the constant. What if it's 1 over 2 on the left of the equal sign? But on the right of the equal sign, it is 3 over 6. What did you multiply by? 3. 3 is the constant. So what's the constant? We're going to call it K. We're going to give it a variable. We call it K in this case. So V over T equals K. And P over T equals K. And P times V equals K. And then in this case, P times V over T equals K. So this gives us, this is what we want to know. So this gives us our constant. Now, this is where it gets fun. Everybody have their imaginary like brain exercise, your imagining parts, imagining muscles.
Yeah.
You're going to need to imagine something here. All right, we have something called an ideal gas law, and it is PV equals nRT. And a lot of people will remember this by calling it PIVNERT. That's fun. PIVNERT. PIVNERT. It's funny, but you can remember PIVNERT, right? Okay, so why is PIVNERT a thing? Why is an ideal gas a thing? Okay, an ideal gas is a conceptual approximation that helps us model and predict the behavior of real gases. What do you suppose is meant by a conceptual approximation? Those are big words.
like kind of it's like exact.
Kind of. So conceptual meaning it's a concept. You're imagining it. An approximation being like an estimate. Basically, there is no ideal gas. It's not a real thing. But it's a concept, an imaginary thing that we can use to predict how real things are going to behave. So it's in an ideal gas, we say that molecules don't attract or repel each other. Do they in real life? Do molecules attract and repel each other in real life? Of course they do. And we also say that gas molecules take up no volume in an ideal gas. But do molecules take up volume in real life? Of course. But we say these things because there's so many variables involved that we can't make all those, we can't do all those calculations, make all those predictions. It's too much. It's more than we know, so we can't do the math. But if we set up an ideal and we go, this is our ideal, this is our imaginary approximation we're going to use, then we can work with it. So that's what an ideal gas is. And you'll see it a lot, you'll hear it a lot. You guys won't work with it too awful much. All right, let's look at these answers. So if the temperature of a gas is constant when the pressure is increased, the volume, Emerson. True. Okay. If the air pressure inside an inner tube is constant when the temperature of the air is increased, the volume, what, Annabelle?
The volume.
Number 2.
Increases.
Increases. Very good. Number 3, the graph of the relationship between the volume of a gas at a constant temperature and its pressure is a line, Everly? It's a curve. If the temperature of a gas inside a sealed rigid container is decreased, its pressure, Emerson. There you go, decreased is true. The graph for Charles's law shows the volume of a gas at a constant pressure is inversely proportional to its temperature. Eunice? It's directly proportional, right? All right, if a gas at a constant pressure inside a cylinder topped by a movable piston is heated, the volume of the gas will do what, Annabelle? It would, yes, it's true. It will increase, push the piston outward. That is how your internal combustion engines work in a car. A gasoline powered car is taking advantage of what's going on in number 6. So you basically have a little bit of gasoline that's kind of pulled out of your gasoline tank and sort of aerosolized, like, you know what I mean? It's kind of sprayed into one of the cylinders of your engine, and your spark plug makes a tiny spark. And then what do you suppose happens to that gas? What happens? It ignites, so it expands rapidly. It's heated, it ignites, boom. It expands rapidly, it pushes that piston up, and that moves your drive shaft. And that's how your car goes forward. Or your truck. That's what's happening. Yep. All right, Everly, when the graph relating two variables is a straight line passing through the origin, the variables are what? Directly proportional. According to which law, when the pressure of a gas at constant temperature is increased, the volume decreases? Emerson. Boyle's law. According to which law, the temperature of a gas is increased at a constant pressure, its volume increases? Annabelle? Charles's law. And when the product of two variables is constant, the variables are, Everly? Inversely proportional, yes. All right. So here we're going to wrap 2 of them together, Boyle's law and Charles's law, but we're going to add in Avogadro's law. Oh, who's Avogadro? Who's that guy? Amadeo. 6.02 times 10 to the 23rd. And what's that number?
A mole.
A mole. Remember our guy who gave us the moles?
Yep.
Avogadro. He's got a gas law too. Okay, so we're going to put them all together here.
There's DIY.
Oh.
And there's doing it.
Well, it's fun to knit. Yes, knitting. Yes, yes. There you go. Oops, I don't know why it starts there. I think I may have accidentally copied it from the wrong place. There we go.
For some reason, that is just weird.
I love TED-Ed.
A weirdly calming aesthetic.
It is a weirdly calming aesthetic, I agree.
In society, we have to follow laws that maintain order. Did you know all chemical matter follows certain laws as well? In fact, we can describe those laws by looking at relationships. Some easy laws to begin with are the ones that govern the gases. Back in 1662, Robert Boyle realized that gases had an interesting response when he put them into containers and changed their volume. Take an empty bottle and put the cap on it, closing that container. Now squeeze your bottle, and what happens? The pressure inside the bottle increases when the size of the container decreases. You can only crush that container so much until the gases inside push back on your hand. This is called an inverse proportion, and it changes at the same rate for every gas. Boyle's law allows chemists to predict the volume of any gas at any given pressure because the relationship is always the same. In 1780, Jacques Charles noticed a different relationship between gases and their temperature. If you've ever seen a hot air balloon, you've seen this law in action. When the balloons are laid out, they're totally flat. Instead of blowing the balloon up like a party balloon, they use a giant flame to heat the air inside that envelope. As the air is heated up, the balloon begins to inflate as the gas volume increases. The hotter the gas becomes, the larger the volume, and that's Charles' law. Notice, this law is different from Boyle's. Charles' law is a direct relationship. As the temperature increases, the volume increases as well. The third law is also easily demonstrated. When you're blowing up party balloons, the volume increases. As you're blowing, you're forcing more and more gas particles into the balloon from your lungs. This causes the balloon volume to increase. This is Avogadro's law in action. As the number of particles of gas added to a container are increased, the volume will increase as well. If you add too many particles, well, you know what happens next. Laws are everywhere, even in the tiniest particles of gas. If you squeeze them, the pressure will increase as the particles are pushed together. Low volume means a high pressure because those particles push back. As the temperature increases, gases move away from one another and the volume increases as well. Finally, if you add gas to a closed container, that container's volume will expand. But be careful not to add too much because otherwise, you could end up with a burst balloon.
Okay, so let's have a look here. You've got a test, right? And this test goes back on the other side of winter break because our unit 6 overlapped winter break. So you're gonna have to look way back, right? So here are the topics that are gonna be on your unit 6 test. You're gonna need to define temperature. Well, let's let them all list and then I'll read through them. They go faster than I can. Wow, that's a lot of things, but it's not that hard because a lot of this you know inherently whether you realize it or not. So let's define temperature as a group. What's temperature? Is the average kinetic energy of the particles in a substance. What's the second law of thermodynamics?
The hotter substance to colder.
Yes, that's the one that you know just because you've seen it 100 times. It's about heat. Thermal energy is always going to flow from the hotter substance to the cooler substance. Somebody tell me what's enthalpy.
Enthalpy is the total energy of the system.
Yep, okay. Let's raise our hands so people have a chance. Good job. States and phases of matter. If I said, if something goes from a solid to a liquid, what is that, everybody?
It's
Solid to liquid?
melting.
Right. What if it goes from liquid to solid?
Freezing.
What if it goes from solid to gas?
Boiling. I mean,
Solid to gas.
Sublimation.
Sublimation. What if it goes from gas to solid?
Deposition.
Deposition. What if it goes from liquid to gas?
Evaporation.
Vaporization, technically, right? Evaporation is the surface, boiling is throughout, but vaporization, technically. And then what is it if it goes from gas to a liquid? Condensation. You got them, right? You got them. And a freezing point is the temperature at which what?
32 degrees.
Well, that's water, but what is a freezing point by definition? It's the temperature at which
is a point
freezes at. So it goes from a liquid to a solid. What is melting point?
From a
Solid to a liquid. Are freezing point and melting point for a substance the same?
Yep.
Think about it. Yes, freezing point, 0 degrees Celsius is going to go from liquid to solid or solid to liquid, depending on whether your thermal energy is increasing or decreasing, right? Right. And let's see, boiling point. Okay, and boiling point again, it when it changes from a liquid to yes, right, condensation point, but we don't talk about that one too much. Phase changes we just discussed. Phases in general, what you would say that the particles in a solid are moving, not moving, vibrating? How would you describe it? Vibrating but fixed in place. And in a liquid, They're moving. What about, the shape and volume of a solid are what?
They're fixed.
They're both fixed. The shape of a liquid is
A little.
its container, the volume of a liquid is fixed. The gas takes the shape of its container, and is its volume fixed? No, right, all right. How about, I said this a minute ago, raise hands. What's the difference between vaporization, between evaporation and boiling? What's the difference? They're both vaporization. All right, Eunice.
Boiling is when water goes from liquid to
Any
gas.
substance,
Yeah, any substance, and when evaporation is when it goes from this floor, and when it goes from
Kind of. Okay, so vaporization is when you're going from liquid to gas, correct?
Yep.
Boiling happens throughout the liquid. Vaporization happens only on the surface. Okay, remember that one. That one will be on your test. What's entropy? Somebody raise a hand. Annabelle.
It's why hot object. It's why put a hot object next to a cold object.
Yeah, if you said it's the amount of what?
disorder.
Order in a system.
Disorder in a system, right? That's what we're looking for, the amount of disorder in a system. What's the relationship between entropy and enthalpy? Somebody raise your hand. If entropy goes up, what happens to enthalpy?
It decreases.
Right, and then Emerson, what happens if your enthalpy goes up? Your entropy does what? Decreases, right, okay. What kind of proportionality is that? Inverse, very good. Charles's law we just did, Boyle's law we just did, Gay-Lussac's law we just did, and ideal gas, you're gonna need to tell me that it's an imaginary concept that we use to predict what a real gas will do. And then definition and equation. I'm gonna need you to recognize PV equals nRT, okay? PV nert, give me your PV nert. All right, so we are good. Let me bring these other people in and we will be wrapping up.
Sounds funny, and now I'm gonna say.
PV nert, yeah.
And now I'm gonna say it in front of my family all the time, and then they're gonna get sick of it.
Yep, that's funny. All right, gang, you wanna come on in?